I'm Peter, a researcher at Google, and I'm very excited to be here with you to tell you all about federated learning and analytics. I'll be mostly focusing on analytics because it's new and very exciting. So the name of the event is Data Council, so I assume we all have interest in data, so let's start with data. And as you probably all know, data is born at the edge. We're talking smartphones, we're talking computers, tablets, all kinds of sensor devices, personal assistants, smart cars, so on and so forth. Lots and lots and lots of data. And this data is very useful to do AI, machine learning, recommendation, personalization, so many beautiful things that we have been accustomed with. However, this data is very sensitive. It captures a lot of our personal information, and it could somehow be damaging if it leaks out to the public or if it's used against us. And so that's, the biggest fundamental question that we're here to tackle. Can we actually leave this data at the edge? Can we still train AI and machine learning models while never collecting and storing the data and putting it in one place? This has advantages for privacy, and this has advantages for other things. It can also improve latency. It can also improve battery life. It can make our services work offline. And so this fundamental question, though it's rooted in privacy, it has very many ramifications. And this is really what led to the birth of federated learning. So what is federated learning? Federated learning is a machine learning setting where multiple entities, they collaborate together in solving a machine learning problem. So they want to train this model collaboratively and collectively. But they do it under the coordination of a central service provider. Okay? So there's a server or a service provider, and that is orchestrating the communication to improve the collaboration between these people. The important part here is that each client's raw data is actually kept locally on the device. It never leaves the device. And somehow we engage in exchanging focused updates for the specific task that we are performing. These are very minimal updates that do not capture a lot of information. They capture the necessary information to design this combined model that the people are engaging in. Now, federated learning appears in two main settings. There's the cross-device federated learning, where we have phones as clients. So here you can imagine you have a very large fleet of devices. We're talking tens of millions or hundreds of millions or even billions of devices. Think sensors, phones, laptops. So this is a very large-scale setting of federated learning, and this is what Google has been largely focused on. But there's an equally interesting setting of federated learning. It's called the cross-silo federated learning setting. And here, we don't have phones or sensors. We have institutions. These institutions can be banks. They can be hospitals. They can be schools. And as you see, we have far fewer institutions or clients here. We're talking maybe tens, hundreds, thousands at most. But each one of them has a lot more data. So compared to a smartphone, a bank will have far more data about far more clients. And so it's a very different dynamic in many ways. Now, in the past, I've heard that this beautiful setting of federated learning resembles distributed machine learning, and it does have some overlap with classical distributed machine learning that perhaps a lot of us are used to. But there are some very important differences that I would like to emphasize. First of all, in distributed machine learning, the data is all placed in one location on the cloud, and the data is shuffled and then partitioned into multiple sets and submitted as jobs to a number of workers. Maybe we have 10 workers, maybe we have 20 workers, 100 workers, but the very interesting thing is that each worker is going to see kind of the same view of the data. This step where we shuffle and mix all the data together and then partition it is going to make sure that each worker is going to get a balanced slice of the data, an equal slice of the data. This is not the case with federated learning, both in the cross-silo and in the cross-device federated learning, because in these two settings, we don't have the luxury of combining the data, putting it in one place, and then shuffling it in order to then partition it and send it into to workers as jobs. There are other interesting differences. You can see them on this slide. Order of devices, for instance, in cross-device, we have millions to billions of devices. The order makes the problem much more challenging because we have far less data per user than we have users. We have many users, and each user can have possibly very few examples. And that leads to, again, a very different optimization dynamic, which we're going to talk about. The idea of possibly keeping track of a state on the client, and if that client participates in multiple training rounds, fetching that state and building on that state to do some local computations, that's very difficult in federated learning. In data center training, we can maintain worker states and things like that. So there are all these nuances that I'm showing on these slides that make federated learning a very unique and important setting of machine learning. There's also a closely neighboring area of machine learning. It's called fully decentralized learning. And that's a very interesting area, but it's very different because in fully decentralized learning, we do not have a service provider. So there's no orchestration back and forth between a server and a fleet of devices or institutions. Here, there's a graph describing interactions between users or clients, and users can talk directly to one another. So you can see that, again, the dynamics are very different. So federated learning is related in some sense, but also fundamentally different from fully decentralized learning. So this is kind of, in a nutshell, an overview of federated learning. And I've largely focused on training models, deep neural networks, and such. But it turns out that federated learning as a concept and a paradigm applies equally well for other operations. One such thing is federated analytics. And this is very similar to learning, but instead of training models here, we may want to do some data science or some statistics. For instance, we may want to compute averages or quantile statistics, histograms, find popular items, all kinds of SQL-like operations, if you may. And that's why here we don't focus very much on neural networks or optimization. We focus on analytics and statistics type tasks. And in fact, in this talk, I'm going to largely focus on federated analytics because it's new and very exciting, and I want to share with you some of our recent work in this space. To be precise, I want to talk to you about this federated heavy hitters discovery problem. So in this problem, we have users, and these users type words on their keyboards. Think about this as Google Keyboard, which is a very powerful keyboard that has a lot of AI and machine learning under the hood. And perhaps Google or a service provider wants to find what are the exciting words that a lot of people are typing. What are those trendy new words? For instance, nowadays people are talking a lot about COVID-19. Soon enough, they'll be talking about the elections. If a celebrity releases a new album, they'll be typing the name of the album or the song or the celebrity. These are new words that trend on a day-to-day basis or week-to-week basis. And so it would be very nice if we can have a process using this federated analytics toolbox in order to find these newly trending words very quickly and very efficiently without invading the privacy of people, without having to collect anything and everything a person types on their keyboard in order to then analyze and find those trending popular words in the population. Now, for the sake of simplicity and to keep things simple and short, in this talk I'm going to focus on the setting where each device has one single word, but everything I'm going to say in this talk applies equally well for the setting where people have many words. So you don't have to restrict a client or a device to have a single word. People can have many words. All right, so the best way to explain our algorithm and to present to you how we're going to go about solving this is to show you an example of how it works, and hopefully you'll get it very quickly. But I'm happy to also take questions after the talk to better explain if concepts that may have been misunderstood. So here's the algorithm via example. Or we're going to assume we have about 20 users, and each user has a single word. You can quickly see from the words that I'm putting up on the slide that moon and sun are popular because they appear 4 times in this very toy example, in this small population of just 20 users. Obviously, in practice, we have hundreds of millions of users, but this is just to illustrate how the algorithm works. Notice that we've added the $sign to the end of every word. This is going to be important because we want to have a method for the service provider to know that we've reached the end of the word, because different words have different lengths. Moon has length 4, whereas other words for instance, that phone number has length 12 with the dashes in it. So different words will have different lengths, and we need to find a way to know that this is the end of the word, okay? So here's how the example is going to, how the algorithm is going to proceed. This is really going to be simple. We're going to proceed in rounds. That's how federated learning in general proceeds, in rounds. And in each round, we're going to do 3 steps. So let's start with round 1. In round 1, the service provider doesn't know anything because it just started this job. So there's no knowledge on the server side, which I'm showing on the left-hand side of the slide. So the first step of round 1 is to select devices. And for the sake of simplicity, I'm going to select devices at random. Say these are the 10 devices that I've selected. These are the devices that I've checked in to our servers that have data that we need to compute on to learn the trending popular words. And so because we are in round 1, we're going to ask the devices to send us the first character of their word. Okay, round 1, first character. And notice what's happening. We're not sending the full word, meaning that we will never capture somebody's social security number, password, first and last name, or bank account number. We're only going to get a single character. So in this case, the selected devices are going to send their first character. We get 3 S's, 2 M's, and then for FGCL6, we get 1 of each. And so the third step of this round is going to be to only keep the popular ones. So what we're going to do is we're going to threshold the counts of the word, of the characters that we got. In this case, I'm choosing a basic simple threshold of 2. In practice, we set it to a much higher number, maybe 20 or 30, depending on the application we're focusing on. But for this toy example, I'm setting it to 2. And you can already see that words that start with anything other than S and M are not going to be discovered by the service provider, because the service provider at this point, after the completion of round 1, learns that only words that start with S or M are popular, because these are the only 2 characters that receive votes above the threshold that we're setting. And so let's go on to round 2. Again, it's going to have the 3 steps. This is round 2, step 1. We randomly select a bunch of devices. Again, for the sake of simplicity, I'm assuming it's 10 devices. And because now we are in round 2, we're going to ask them to send us the second character. So round 2, second character. But here's the caveat that's very important for privacy. Any device that has a word that starts with a character that has not been learned by the server remains silent. So if you have a word such as LOL or great in this example, you're selected and you have those words, they don't start with an S or an M, you're not going to send back any update. And that's how we make sure that words that have prefixes that are not popular are never discovered by the service provider. So in this case, we're going to get votes or counts on words that start with S or M. And as you can see, here we get 3 for SU, 2 for ST, and 2 for MO from the fleet of devices that we've randomly sampled. Again, the last step in this round is the threshold, and it so happens that in this case, all these prefixes have received counts above our threshold, or above or equal to our threshold, 3 or 2 votes. And so we're going to add them to the tree of prefixes that we're building interactively. We can run more rounds. This is, again, for illustrative purposes. I'm going to run a 3rd round and then a 4th round. Notice what happened in round 4. We would have liked to learn star, but we didn't get enough votes on the prefix STAR. So that's why the character R is not added to this tree that we're building interactively on the server. And so that's unfortunate. And then at the end of round 5, you can see that the server has learned the word sun and the word moon, and these are 2 popular words in this fleet of devices. So we're happy that we were able to learn these 2. And anything that is not popular was not learned. And the way we know that we've learned sun and moon is because we've hit that dollar symbol that denotes the end of the word. And that's why it's important to have that symbol added locally to the words that clients have. So this is the algorithm in a nutshell. What I've just described is very general. It does not only apply to words, it can apply to any string of bits or any string of characters of any sort. So you can use it for URLs, you can use it for all sorts and all kinds of things. It can also be used for location, because we can encode location via lat, comma, long, longitude. And so we can do a lot of things with it to discover popular hotspots for COVID-19, trending words, popular URLs, popular clicks, anything and everything that is new and we would like to discover. Now, this has been published in AI Stats 2020, so you can grab the paper and learn more about it. You can ask me questions after this talk if you want to learn more. But what I want to emphasize and focus on in this talk is the inherent privacy guarantees that we get automatically if we use this algorithm, this TrieHH algorithm, as we are calling it. So notice that we are getting structural k-anonymity, and the reason why we get this k-anonymity concept is because in every step of the algorithm, we're thresholding the prefixes. So we're ensuring that any prefix that appears less than theta times, in the example, it was set to 2. In practice, you set it to a larger number. All these are thrown away. We don't keep them in the data structure, and we don't continue to extend them. And that's why we are going to get k-anonymity. At the end of the day, any string that we discover, any word that we discover, is going to appear at least theta times in the population. In fact, it's much stronger than that. It turns out that, with a lot of theory and, it was a little difficult, but we were able to prove that this algorithm end-to-end achieves differential privacy. Now, differential privacy may not be a concept that is popular to everybody in this room. And so all I'm going to say is that it's the gold standard of privacy these days. And it's a very mathematically elegant way to rigorously quantify information leakage. And hopefully, a lot of us have seen it in the past. We usually measure differential privacy properties of an algorithm via 2 parameters. They're called epsilon and delta. And ideally, we want both to be very small. We want epsilon to be on the order of a single digit, something like maybe 2, 4, 8, something like that, single digit number. We want delta to be inversely proportional to the size of the population that we have. So something like 1 by n, where n is the size of the population, or maybe even better if it's 1 by n squared. So something 1 over a quadratic of the size of the population. That's even better for delta. And so what you're seeing as a table on the right-hand side is essentially how we can tweak the knobs of the algorithm in order to achieve an epsilon of 2 and a delta that scales as either 1 by n or 1 by n squared. These are very strong parameters for differential privacy. And you can see that for different population sizes, we're starting with 10,000 up to 10 million. We can set our thresholds and the fraction of users we're going to select to some reasonable numbers in order to get those strong differential privacy guarantees. And I'll show you in a bit that we also get good utility, and that was the main motivation behind this algorithm, because we didn't want to let go of utility and accuracy. That was really important. And as you saw, because we're asking devices to remain silent if they do not have words that start with prefixes that have been discovered in previous rounds, that's why we have limited exposure to the server. So that's actually a very good property in this federated analytics or federated heavy hitters approach. All right, so I told you I wanted to show you utility, and we've done experiments on a massive data set. It's called Sentiment 140. For those of you who have done natural language processing research or engineering in the past, they may be very well aware of this data set. It's a Twitter data set, meaning that it has tweets from almost about 600,000 users. It has about 1.3 million tweets. It's a fairly large data set, and it makes a very nice data set for federated analytics because the data is already keyed by user. So we know for each user the tweets that they tweeted. And so it captures the imbalance in the data. It captures the fact that each person has very few tweets. And we've ran our algorithm, and we've compared it to what's shown as SFP. SFP stands for Sequence Frequency Puzzle. It's an algorithm by Apple for discovering out-of-vocab popular words. And we're doing a comparison with them by showing the performance of our algorithm, which is TrieHH, to there. I'm plotting the F1 score as a function of top K. So on this x-axis of this plot, I can either focus on the top 100 words in the data set, or top 200, 300, so on and so forth. And I can compute the F1 score, which is geometric weighting between precision and recall, how accurate I can discover these top words. And as you can see, with strong DP guarantees, TrieHH performs really well for the top almost anywhere between 100 to 200 words. Whereas sequence frequency puzzle drops very sharply after 20 or so, 25 or so. And you can find a lot more results and details in our paper. All right, so I described the strengths of the algorithms, and the mechanics of the algorithm. It's a beautiful algorithm, but it does have some weaknesses. And let's talk about them right now. So the first weakness is that in every round, the devices that are participating are sending those character extensions. Some of them will remain silent, and that's okay, and that's great for privacy, but some of them are actually sending in clear those characters to the server. So the server can actually link that I got this character from this person. And that leaks some information. Again, it's not a lot of information because we're making sure that the tree of prefixes that we're building only retains those popular prefixes, but still you can link devices to their characters, and that's not okay. But there's a quick fix for this. We can use a technology called secure aggregation. Secure aggregation is a multi-party computation technology that allows the service provider to only see results in aggregate. So instead of the service provider being able to inspect every update that it gets from every participant, it will only be able to see the aggregated votes. In this example of this algorithm, TrieHH, the algorithm will only allow the service provider to see that the character S got 4 votes and the character L got 5 votes, for example. But it wouldn't know who voted on which character. And that's one way to address this issue. Now, there's another issue or weakness for this algorithm, which is that all the privacy properties that I've described, be it differential privacy or even k-anonymity, and all these beautiful properties that we get, apply for the thresholded tree, which is the one that I'm showing on the left-hand side. And this is, by the way, the data structure that we're going to pass on to engineers at Google that are trying to do the analyses over these popular strings or words. And so we're happy about that because we're limiting exposure drastically. Pretty much everybody working on a machine learning team will only see the final outcome, the thresholded final outcome, and we'll get those strong privacy guarantees, k-anonymity and differential privacy. But we can still say that what if the server is compromised? The server sees a bit more. The server sees those character extensions that did not get counts or votes above the threshold. And so maybe pathologically, in the worst case scenario, having that extra character added to the tree might leak some information. Again, one could construct these perhaps worst case pathological examples. And so there's a solution for this, and I'll tell you about it in a bit. We can fix this. Finally, another assumption that I've made in this talk is that the server can sample devices uniformly at random. If you go back to this toy example, I was selecting 10 devices at random, and it was like uniformly at random. It turns out that this uniform property is needed for some of our DP proofs to go through. If we don't have uniformity, we believe that we're still going to get differential privacy guarantees, but the math is going to be far more complicated. And again, there's a way to address this issue, and you'll see it in just a slide. So this is what we're going to call Hardened TrieHH. So the previous algorithm that I described is TrieHH. This version of TrieHH is the hardened version. And the reason why it's hardened, to address the two issues on the previous slide, is because we're going to ask users to introduce randomness into the process. Meaning that when they are asked to vote on the tree of prefixes, sometimes, occasionally, they will send a character extension even if they don't have it. You can see those red arrows and red characters that have been added to the tree on the left-hand side of this slide. And that means that with some very low probability, a user is going to send a character that they do not even have. And sometimes, even if you have a character extension on an existing prefix in the tree, you may choose to remain silent. So you can flip a biased coin and say, all right, even though I have the extension, I'm not going to share it. This introduction of some randomness is enough to provide strong differential privacy guarantees without even having to rely on uniform sampling, that assumption that in production is not correct all the time, at least, and to give guarantees also with respect to the service provider. Now, I'm not going to dig deep into the details of how we construct these randomization because I'm going to run out of time, but I'm happy to talk more about this during the Q&A session. There's a lot to talk about, both for federated analytics and federated learning. I'm going to end my talk on this note. We put up a paper with 58 authors. A lot of these people are top-notch academics and top-notch researchers. The paper discusses many of the advances in this field and outlines a number of high-impact open problems. It's on arXiv. I have the link on this slide. I strongly encourage you to check it out if you want to learn more about federated learning and federated analytics. I'm going to end here and thank everybody for attending this talk.